So quick review of bond energy. Let's say you've got some cluster of n moles of atoms in, let's say, a solid form. If you wanted to figure out what the bond energy is, what information would you need to know in order to calculate the bond energy of those n moles of particles? Like if you just got some cluster of particles, presumably several moles of them. So this is an enormous quantity of particles. We're only just drawing out a small subsample. What information would you need to know about those particles in order to find the bond energy?
The distance separating the atoms?
Yeah, we want to know something about distance. Presumably the distance, if we're talking about nearest neighbors, presumably those are all equilibrium distance. So let's say all of these nearest neighbors are not from each other, which means the energy of each one of those nearest neighbor bonds would be what?
Should be
what do we call the energy of one bond? Yeah, negative epsilon. So the energy per bond is negative epsilon. If we want to find the total energy of all the nearest neighbor bonds, we just need to take negative epsilon multiplied by the number of bonds. And we can find the total number of nearest neighbor bonds by looking at the number of nearest neighbors for any one particle. Like let's say this one particle has maybe 5 nearest neighbors, or however many nearest neighbors each particle has on average. How do we go from number of nearest neighbors one particle has to the total number of nearest neighbor bonds in the whole system?
you would count them up and then take care not to double count the bonds?
Yeah, we want to make sure we don't double count. So we're gonna, how do we generally go from, so we may need to divide by 2 to eliminate double counting. But how do we calculate the total number of bonds in the first place? Like let's say we know the number of bonds each atom has. Then what do we do with that number?
Oh, just multiply the number of bonds one atom has times how many moles you have.
Yeah, number of bonds per atom, or per particle, I should say. They might be atoms, they might be molecules. Multiply that by, we want to multiply that by the total number of molecules. And how do we convert number of moles to number of molecules?
Number of moles times Avogadro's number.
Yeah. So Avogadro's number of moles times Avogadro's number, that's the number of particles. Multiplied by number of bonds per particle, that tells us the total number of bonds. Although that does double count, because if we say like, let's say this atom has 5 nearest neighbors, and this atom has 5 nearest neighbors. We just counted that bond twice. So in a context like that, you would need to divide by 2. And I would recommend checking every time. Anytime you've got some sort of diagram showing the structure of the atoms, try just picking a couple of adjacent atoms and say this atom has however many nearest neighbors, and actually drawing those bonds. Then look at one of its neighbors and say this atom has however many nearest neighbors. If you've just drawn a certain bond twice, that means you've double counted. So you need to divide the result by 2 to eliminate that. So this should be the total number of bonds of that type. We can then multiply that by the energy per bond. And this would tell us the bond energy of the entire cluster. And of course, this is only looking at the nearest neighbor bonds. If you wanted to also include second nearest neighbor bonds, you could use the same structure. Number of second nearest neighbor bonds per particle. So for any given particle, you look at how many atoms are there that are a little bit further away, times Avogadro's number times number of moles divided by 2. And then instead of multiplying by negative epsilon, you'd be multiplying by negative some fraction of epsilon. And that fraction is going to be based on the distance between those particles. And they're a little bit further apart, so the bond is going to be a little bit weaker. But you can look up the amount of energy on the Lennard-Jones potential graph or use the Lennard-Jones equation. Any other questions on that so far?
Thank you.
So this is generally a a formula for at least estimating bond energy. It's ignoring edge effects. It's ignoring anything beyond the nearest neighbors, but it's still going to be pretty close. Next to the Avogadro's number, this is lowercase n, which is number of moles.
Does N sub A always stand for Avogadro's number?
Yeah, this is a reserved symbol. N sub A is 600 hextillion, the number of molecules in 1 mole. Well, approximately 600 hextillion. So that's you can almost think of Avogadro's number as a conversion factor. It's the conversion factor between number of moles versus number of molecules. 2 different ways of measuring how much of this stuff you've got. In fact, in a lot of ways, mole is kind of like dozen. Like dozen just means 12 of something. Mole just means 600 hextillion of something. Any other questions on that? And this also plays into the idea of delta H, the heat of melting or heat of vaporization. For instance, if you want to vaporize this whole substance, you would have to add this amount of energy, but plus epsilon instead of minus epsilon. So to break all the bonds, you'd have to add this much as an absolute value. Number of bonds times Avogadro's number times n over 2 times epsilon. So you'd have to add this much energy. But delta H, or at least delta H mole, the molar heat of vaporization, is the amount of heat you'd have to add per mole. So if we're looking at, if we want to standardize this for exactly 1 mole, because this is really what delta H and heat capacity and stuff like this are all about, standardized to 1 unit of the substance. If we standardize this to exactly 1 mole, delta E bond to break all the bonds would be this, but with 1 for n. So number of bonds times Avogadro's number times epsilon over 2. And this is what we call delta H mole. The molar heat of vaporization is literally just the amount of energy it takes to break all the bonds in 1 mole. So you could think of that as just delta E bond is 1 times delta H mole, because we're talking about 1 mole. Any questions on that bond energy stuff so far? Then let's try applying this same approach to thermal energy. So thermal energy is the kinetic and potential energies of the individual particles as they wiggle around. So if you just have some particle,
I have a question real quick.
yeah,
Did you say that thermal energy is the kinetic and the potential energies?
yeah, because if you have, at least for solids and liquids, let's say, if you've got a solid or liquid, if you add heat to the substance to warm it up, macroscopically, you're raising the temperature and the thermal energy. Microscopically, though, what's actually going on with the molecules, as you raise the temperature, what's happening to the behavior of the individual molecules? What are they doing differently?
Very generally, they're moving faster.
Yeah, they're moving faster, so that's an increase in the kinetic energy of the individual molecules. Also, as we saw in the Lennard-Jones potential graph, when you raise that total energy, the R min gets a little closer, the R max gets a little further. So they're moving faster on average, and they're getting closer together and further apart on average. So you're increasing both the kinetic energy, because they're able to move faster, and increasing the average potential energy, because they're able to get closer and further from each other. So when we talk about thermal energy of the whole object, we're really talking about both the kinetic energy and potential energy of the individual molecules. And we usually categorize this in terms of this idea of modes. a mode is an independent way for a particle to have energy. Also known as degrees of freedom. And by independent, we basically just mean they don't influence each other. So we're going to consider kinetic energy and potential energy separately. And also anything that's perpendicular to each other counts as independent. So for instance, a particle moving in 3 dimensions can have kinetic energy along the x-axis and kinetic energy along the y-axis and kinetic energy along the z-axis. Those count as 3 separate modes because these 3 perpendicular dimensions don't directly influence each other. They count as independent. So since the particle can move in 3 dimensions, it has 3 translational kinetic energy modes. And those count as kinetic energy because the particle is in motion. And that's going to be always the case. Anytime a particle is able to move, it's always going to have 3 translational modes, unless it can move only in 2 dimensions. For instance, if you're talking about a hypothetical alternate universe that's just 2-dimensional, it's only got x-axis, y-axis, but no z-axis. In that case, particles would only have 2 translational modes. But if it can move in 3 dimensions, it has 3 translational modes guaranteed. Also, in a solid or liquid, the particles can interact with their neighbors. So what other types of energy would it have if it can interact with its neighbors? What type of energy involves, vibrational energy, which is a form of potential energy. And by vibrational, we basically just mean the interaction with its neighbors. So we would have, and this, I often call this external vibrational to distinguish it from the vibration going on inside the molecules. And this counts as potential energy. So this is interaction with other molecules nearby. And since we're in a 3-dimensional universe, this would also come in sets of 3. One molecule can interact with its neighbors to the left and right, can interact with its neighbors in front and behind, and can interact with its neighbors above and below. The usual metaphor for this is that you can think of each particle as if it's attached to 3 tiny invisible springs, a spring along the x-axis, a spring along the y-axis, and a spring along the z-axis. As it oscillates around, each one of those invisible metaphorical springs is associated with kinetic energy and potential energy. So we've got 3 of each, kinetic energy and potential energy along each axis. However, it's only going to have the ability to interact with its neighbors under what circumstances? Or can you think of any circumstances where a molecule wouldn't be interacting with neighbors?
If they're unbonded, they're not going to be interacting with neighbors.
Yeah, if they're unbonded, if they're in a gas phase, then there are no nearby neighbors. They're too far apart. So this 3 external vibrational modes only applies if it's in a bonded state, solid or liquid. So if it's a solid or liquid, it would have 3 external vibrational modes. It would have none if it's in a gas. Because in a gas, we're assuming the particles are so far apart that they're not interacting in a meaningful way. They are, of course, still exerting forces on each other. It's just that those forces get so small when they're far apart that we can ignore those forces. Any questions on those so far? And for solids, these are typically the only modes you would consider. For solids, we would basically just treat it as if it's monoatomic. If it's a gas, though, especially if it's a diatomic or larger, then we've got some other possibilities to consider. So a monoatomic gas would have just the translational modes, 3 of them, and that's it. But if it's diatomic or larger, like let's say, for instance, you have, let's say a nitrogen molecule. This nitrogen molecule could be moving around in space, so it's got the 3 translational modes. It's got no external vibrational modes because it's got no neighbors to interact with. But how else could this molecule be moving other than translational? Yeah, it could have rotational modes. It could be rotating, spinning around some axis. So rotational modes are another one we need to consider. And would those count as kinetic energy or potential energy? Yeah, it involves motion, so that's going to be kinetic energy. Rotational kinetic energy as opposed to translational kinetic energy. The energy of rotational motion, spinning in place. And of course, it's really doing both. It's spinning as it moves, so it's sort of tumbling along through space. And how many different axes could this rotate around? Yeah, just 2. Usually we'd expect 3 axes because we're in a 3-dimensional universe. But what's special about this molecule that makes it only 2 axes of rotation?
It's symmetric to one axis.
Yeah, it's got this symmetry around an axis, specifically around this axis here. If you take this linear shaped object and try to rotate it around that axis, like if I'm just rotating this marker around this axis, nothing's really changing. As opposed to, like, let's say I rotate it around a vertical axis. This rotation around a vertical axis, and it's definitely changing. Each atom in it is actually moving. Or if I rotate around an axis sticking straight out of the board, this counts as rotation. This is something actually changing. But if I try rotating around its own axis of symmetry, it's not actually moving in a meaningful way. So rotation along its own axis of symmetry doesn't count. So this would only be 2 rotational modes. What would have to be true in order to have all 3 rotational modes?
It would have to be non-linear,
Yeah.
or at least asymmetrical.
Yeah, and in this case, the symmetry we're talking about is it linear in shape or is it nonlinear in shape? No matter how large the molecule is, if all the atoms in the molecule are along a straight line, then you don't have that 3rd rotational mode. You'd only have 2. But if there's even one that's off the straight line, if you've got like a molecule that's entirely arranged on a straight line, except for one atom that's off the line, that makes it nonlinear. If there's any atoms that are off of that straight line, that is a nonlinear molecule, and so it would have 3 rotational modes. So rotational modes, you could have 2 if it's linear in shape, or 3 if it's nonlinear. Or one final situation, what if it's monoatomic? If you just got a single atom, are there any axes that could rotate around in a meaningful way? Not really. It's symmetric. It's got radial symmetry around every axis. So whatever axis you try to rotate it around, nothing's really changing. A perfectly smooth sphere doesn't really change as it rotates. So we don't really count that as a meaningful rotation. So for monoatomic, we would say no rotational modes ever. Also, for any of these, we would say, if we're talking about extremely cold temperatures, it turns out that at the molecular level, do you remember the idea from chemistry of electron orbitals only existing at certain values of energy? Like if you've got an electron with a certain amount of energy, if you add enough energy to bring it up to the next level, it'll jump up to the next level. But if you add part of that energy, it doesn't go part way up, it just doesn't go anywhere at all. That the energy can only exist at certain specific values. It turns out that at the molecular level, most types of energy behave like that. That there are certain values of rotational energy it can have, but it can't have in-between values. And this is very unlike macroscopic objects. Like a macroscopic object, if you've got like a marker hanging from a string and you start spinning it, you put a certain amount of energy into it and it starts spinning at a certain rate. If you were to put less energy than that, it would just spin slower. But it turns out at the molecular level, there's a certain minimum amount of energy required to spin at all. If you put less energy into it than that, it doesn't spin slower, it just cannot spin because there's not enough energy to get it spinning at all. So if the temperature is too low and there's not enough energy per molecule to make them spin, then it just doesn't have any rotational modes. So if we're talking about very cold temperatures, like significantly below room temperature, then the molecule just doesn't have any rotational modes at all. And we would say the rotational modes are frozen out. So frozen out, modes that are frozen out means that the temperature is so low, there's not enough energy for those modes to exist. And so those modes just don't happen. Very cold molecules do not rotate. But once you get up to about room temperature, you can assume that the molecules are able to rotate, at least for diatomic molecules. The exact threshold of can rotate versus can't rotate varies from molecule to molecule. But diatomic molecules in a gas form, we usually assume they can rotate by the time they get up to room temperature. Any questions on that so far? And then one other type of mode we should consider is this idea of internal vibrational modes. The external vibrational modes were like a molecule interacting with other molecules nearby. Internal vibrational modes are the individual atoms in a molecule interacting with each other inside the molecule. So for instance, if you have a molecule, let's go back to that nitrogen molecule from earlier. Within this molecule, this nitrogen atom and this nitrogen atom can be vibrating against each other. The molecular bond acts like a tiny invisible spring also. So there could be oscillations going on inside this molecule. And if these molecules vibrate against each other, if they're actually oscillating, what types of energy would they have?
Vibrational.
We would call this vibrational energy overall, yeah, and we'd specifically call that internal vibrational modes, as opposed to external vibrational. So external vibrational modes are the molecule interacting with other molecules nearby, if there are any. Internal vibrational modes are the atoms in the molecule interacting with each other. And since they're in motion, they have kinetic energy. Since they're interacting with each other, they have potential energy. And so the internal vibrational modes, we usually just lump together the kinetic and potential energy of that vibration. Sometimes we do that with these also. Sometimes we would call the translational, the kinetic and potential energy modes, we would just lump those together as the external vibrational modes. I usually find it's a good idea to treat them separately. But the internal vibrational modes, we usually include both kinetic and potential energies. And to count those, how many dimensions is the oscillation of these two particles?
3 dimensions?
There is
Actually, no, 1.
3 dimensions, but the thing is we've already counted some of them. For example, let's say these particles are, they can move in 3 dimensions individually, but let's say both particles happen to be moving upwards. If both particles are moving upwards, that means the whole molecule is moving upwards. And we've already counted that as translational modes. Or let's say one particle is moving upwards and the other particle is moving downwards. In that case, what's the overall molecule doing?
Rotating.
Yeah, that's a rotation, and we've already counted that as well, or here, rotational modes. So we don't want to count again modes that we've already counted. So both particles moving in the same direction, or particles moving one up and one down, or one forward and one backward, those just count as rotational modes. So many of these modes we already counted. All that's really left is if they're moving towards each other or away from each other. So if these particles are moving both towards each other or both away from each other, those are actually modes we haven't counted yet. Moving towards each other and away from each other, but that's only 1 dimension. So since the only motion we care about for internal vibration is along that 1 dimension, we can treat this as a 1-dimensional oscillator. It has 1 mode of kinetic energy, because they could be moving along this 1 axis, and it has 1 mode of potential energy, because they could be interacting with each other along this 1 axis. So for a diatomic molecule, we'd say it has 2 internal vibrational modes. And again, this is only if the temperature is hot enough. At cold temperatures, in fact, at around room temperature, there's not enough energy for this to vibrate internally at all. So the internal vibrational modes are only active at higher temperatures. If it's too cold, usually including room temperature, we would say these modes are frozen out. And again, the exact temperature at which they become active varies from molecule to molecule. It's really more of a gradual transition, in fact. As you're raising the temperature higher and higher and higher, it's not like all the nitrogen molecules suddenly activate their vibration at once. It's that you raise the temperature higher, some of the molecules start vibrating, the other ones don't. And then raise it a little higher, a few more molecules start vibrating, and so on. So it's more of a gradual transition if you're looking at the average number of modes per molecule. But any single molecule, it's either vibrating or it's not. There's no in between there. So this molecule, this nitrogen molecule, if we wanted to count up all of its modes, let's say we've got N2 gas. We've got to include the 3 translational modes. Should we include external vibrational modes? No, not if it's a gas. So we would ignore those. Rotational modes, how many would we expect? Yeah, it's linear in shape. It's got that linear symmetry. So we have 2 rotational modes. And as we just saw, we should expect 2 internal vibrational modes as well. 1 kinetic and 1 potential. 2 internal vibrational modes. So how many modes would we expect this molecule to have?
7.
Yeah, looks like 7. Or I would say up to 7, because that would only be if they're all active. It's possible that maybe this is a very cold molecule. Maybe we've got very cold nitrogen gas, in which case the rotational and vibrational modes would be frozen out. There's not enough energy to activate them. So at very low temperatures, the nitrogen gas would have only 3 translational modes, and that's it. If we raise the temperature up to about room temperature, the molecule is able to start rotating. So we'd have 3 translational and 2 rotational for a total of 5 modes per particle. If we make it way hotter than that and unlock the vibrational modes, we have 3 plus 2 plus 2 for 7 modes total. So any single nitrogen molecule could have 3 or 5 or all 7. So those would be the possibilities of number of modes for that one gaseous nitrogen molecule. And the 2 internal vibrational modes, this is not so much for linear, this is specifically for diatomic. If the molecule is exactly 2 atoms and that's it, you're going to have 2 internal vibrational modes. If it's larger than diatomic, then it gets more complicated. But let's take a look at that. Before we move on, are there any other questions on these types of modes so far? So let's investigate a larger molecule. Polyatomic. Let's say we have a molecule consisting of, let's say, 7 atoms. And I'm not expecting this to be any sort of realistic molecule. And in general, just some molecule with 7 atoms that happens to be shaped like this. It's nonlinear, so we're able to rotate in 3 dimensions. It's able to move in 3 dimensions, so it's got the 3 translational modes, 3 translational modes, 3 rotational modes. And assuming it's a gas, it would have no external vibrational modes. In order to figure out the internal vibrational modes, though, we don't want to try counting up by hand all the ways the molecule, the individual atoms could move. We don't want to say like, well, these ones could be vibrating against each other, these ones could be vibrating against each other, this angle could be flexing. It's going to be a nightmare to try and count up all the vibrational modes manually. So instead, we want to look for a mathematical pattern that allows us to predict that without having to list them all out. And what we can do is look at this from a different perspective. Instead of looking at it as all one big atom, we could take a look at each individual atom. Sorry, instead of one big molecule, look at each individual atom. Each atom individually if you just consider one atom on its own, how many translation or how many kinetic energy modes would you expect that one atom to have?
3.
Yeah, it's able to move in 3 dimensions. Ignoring the bonds for the moment, this atom is able to move in 3D. So each atom individually should have 3 kinetic energy modes. And how many atoms do we have here?
7.
Yeah, we've got 7 atoms in this molecule. So looking at this on an individual atom basis, 7 atoms, each one should be expected to have 3 kinetic energy modes. So 3 kinetic energy modes per atom. 7 times 3 gives us 21 modes. So if we treat these atoms as individual particles, we should expect 21 kinetic energy modes. But we've already counted some of those modes. Some of these 21 modes happen to involve all 7 atoms moving in the same direction. Those would really count as what type of modes? If all the atoms happen...
Translational.
What was that?
I said translational.
Yeah, if all the atoms happen to be moving in the same direction, we would just say the whole molecule is experiencing translational motion, and we've already counted the 3 of those. Or if, for instance, these atoms are moving upwards while these atoms are moving downwards, what's the molecule really doing?
Rotating.
It's rotating.
If these ones are all moving upwards while these ones are all moving downwards, the molecule as a whole is rotating, and we've already counted the rotational modes. So we don't want to count these in extra time. We want to take the 21 possible kinetic energy modes and subtract the modes we've already counted. So we've got, we expect 21 modes. We expect 21 modes. Or I should specify kinetic energy modes. But we already counted 6 of them for the whole molecule. So we expect 21 based on each atom having 3. We already counted 6 for the whole molecule. So if we subtract those, 21 minus 6 would be 15. That means there's 15 kinetic energy modes we haven't accounted for yet. So we've got these extra 15 modes that don't count as translational for the whole molecule and don't count as rotational for the whole molecule. These are the vibrational modes. These 15 extra modes represent the fact that the atoms in the molecule could be jumbling around without the whole molecule translating or rotating as a result. So we would say there are 15 kinetic energy internal vibrational modes. But we also need to consider the potential energy internal vibrational modes. And those are going to be an even match. We're going to have the same number of potential energy modes as kinetic energy modes. If these atoms can be vibrating against each other in a way that has 15 different ways of having kinetic energy, that has to be paired with also 15 ways to have potential energy. Because we're still treating this as like tiny invisible springs. If we find that there's 15 extra kinetic energy modes, that means these are acting like they're connected by 15 tiny invisible springs. And those 15 tiny invisible springs, each one has kinetic energy and potential energy. So we should also consider 15 extra potential energy modes. So these together are the internal vibrational modes. So 30 internal vibrational modes. So this 7-atom molecule is going to have 3 translational modes, 3 rotational modes, and 30 internal vibrational modes. Any questions on that so far?
How we're gonna have 15 vibrational kinetic energy modes if there's only 6 bonds in the
There's
molecule?
only 6 bonds, but the number of kinetic energy modes or potential energy modes isn't really about the number of bonds. It's more about the number of different ways the particles can interact. So those might include things like maybe these 2 atoms are vibrating back and forth against each other. Maybe these 2 atoms are vibrating back and forth against each other. Maybe this angle is flexing because the angles are flexible. And so if you make this 3-dimensional or 2-dimensional, it becomes much more complicated than just a 1-dimensional system, because you have things like angles becoming flexible and these atoms oscillating against each other, even though they're not bonded. So the number of bonds does not correlate to the number of modes. It's really more about the way the particles are arranged and how many ways there are to interact with each other.
Interesting, thank you.
Mm-hmm. So we end up with 36 modes altogether. And again, that's only if you're at very high temperatures. At low temperatures, you'd expect the translational modes, maybe the rotational modes, but these extra vibrational modes don't activate unless the gas is at higher temperatures. So let's see if we can generalize this. In this case, we were specifically assuming 7 atoms, but we could have a molecule with any number of atoms. So to generalize that, let's see if we can go through this same process. But let's say we have n atoms. So a molecule with n atoms, where n could be any whole number. N atoms times, we're still assuming each atom has 3 kinetic energy modes. So we've got 3n kinetic energy modes, where again, n is just the number of atoms in that molecule. But how many modes have we already counted?
6.
Yeah, in this nonlinear molecule, we've already counted 6 modes. So we would deduct 6 modes already counted. Those are the 3 translational modes and 3 rotational modes. So we expect 3 n modes from the fact that we've got n atoms. We deduct the 6 modes we've already counted. And that means we have 3n minus 6 extra kinetic energy modes. So 3n minus 6 would be the number of internal vibrational kinetic energy modes. But those have to be paired with the same number of what else?
Vibrational potential energy modes.
Right. We've got the same number of extra potential energy modes. Or to put it another way, you could just take the 3n minus 6 and double it. So 3n minus 6 plus another 3n minus 6 would be 6n minus 12 internal vibrational modes. So in general, for a molecule with n atoms, you can expect 6n minus 12 internal vibrational modes. Or if we just want to count all the modes, we would add 3 translational modes plus 3 rotational modes plus 6n minus 12 internal vibrational modes and get a total of 3 and 3 is 6, which partially cancels out the minus 12, so we just get 6n minus 6 modes. So for a polyatomic gas, we can expect 6n minus 6 as the number of modes per molecule if it's n molecules. Any questions on how that works out so far? One other thing we need to be careful of, what were we assuming about the shape of this molecule? Yeah, we were assuming it's nonlinear. A nonlinear gas. So we're going to need to do this differently if it's a linear gas. Fortunately, if it's a linear gas, what's the only thing that's really going to change? For a linear gas, we would have only 2 rotational modes. So let's say we're taking a look at a linear gas. If we just snip off all of the atoms that are off the main straight line, then we're going to have 2 rotational modes, which means instead of deducting 6, we're still going to have 3n kinetic energy modes expected. But instead of deducting 6, we'd only be deducting the 5 kinetic energy modes we've already counted. So that's going to change the results. We will instead have 3n minus 5 extra kinetic energy modes, because the 3n we expect minus the 5 we've already counted, 3 translational, 2 rotational. And likewise, that would be paired with 3n minus 5 extra potential energy modes. So instead of having 6n minus 12, we combine these to what?
6n minus 10.
Yeah. 6n minus 10. And likewise, we want to modify this. We still have 3 translational modes, but we'd only have 2 rotational modes. So if we add these up, 3 and 2 combine to 5, partially cancels out the minus 10 to get minus 5. So we get a total of 6n minus 5 modes if it's a linear gas. So for a linear polyatomic gas, we would expect 6n minus 5 modes if they're all active. For a nonlinear gas, we'd expect 6n minus 6 modes if they're all active. And I would recommend running through this process at least a couple of times yourself just to make sure you're familiar with it. But in the long run, if we just need to know how many modes does this molecule have, we would typically be using one of these formulas. Use these equations for any gas in a given problem? Yes, as long as you know that all the modes are active. In fact, we could even try applying this to the diatomic gas we were already looking at. If we want to apply this to, let's say, just that diatomic nitrogen that we were looking at earlier. Earlier, we were saying this has how many modes? If you count up all the modes you would expect, yeah, 7. You've got the 3 translational modes, 2 rotational modes because it's linear, and 2 internal vibrational modes because the atoms can vibrate against each other in 1 dimension. So 7 modes total. Alternatively, if we try applying this formula here, and actually, which one of these formulas should we be using? 6n minus 5 or 6n minus 6? Yeah, 6n minus 5 because that's the linear case. So 6n minus 5. And what's n here? N is 2 because we just got 2 atoms in the molecule. So 6 times 2 minus 5. That's 12 minus 5, which is 7. So this formula correctly predicts that this diatomic molecule has up to 7 modes. And I say up to 7 modes because it might only have 3 or might only have 5 if it's cold enough. But as long as it's hot enough, as long as the temperature is high enough for all the modes to be active, it will be 7 modes per particle. And so you can apply these formulas to anything, basically anything larger than a single atom. A single atom, you would expect to just have 3 translational modes, and if it's in a solid or liquid state, also 3 external vibrational modes. Monoatomic gas would have only the 3 translational modes, and that's it. But these formulas can be used to predict the amount of modes you would expect from a larger molecule without having to count them all up manually. Any other questions on that?
So what happens when, say, like vibrational kinetic energy modes are frozen out?
That basically just means that the temperature is low enough that there's not enough energy per molecule for them to happen. So at low temperatures, we would expect that the molecule is just not, the atoms in the molecule are not vibrating. That we treat this as just a rigid bond, no vibration at all. And likewise, if it's really cold, there's not enough energy for the molecules to rotate. So they're still drifting through space, but they're not rotating as they do so. They're only going to be rotating if there's enough energy for them to do so. And that's only going to happen if the temperature is high enough.
Okay, so then if there's modes that are going to be frozen out, then we can't use those equations.
Right. In fact, the thing is, these equations are really only important because it's difficult to count up the internal vibrational modes. If it's cold enough that there are no internal vibrational modes, you just say there's 3 translational modes, there's 2 or 3 rotational modes, depending on linear or nonlinear, and that's it.
Got it. Thank you.
So if it's too cold for the molecules to vibrate, you don't need to worry about these equations at all. It would just be 3 or 5 or 6 modes, depending
Got
on.
it.
But if it is hot enough to vibrate, these equations form a really useful shortcut for counting up the total number of modes without having to individually look at the different types of modes. The formula just lets you jump straight to the number of modes per molecule if they're all active.
Why would the particle still rotate if it was frozen out? I thought it doesn't do that at cold
Well, it depends on the temperature. If you're talking about very cold temperatures, then the rotational modes and vibrational modes are frozen out. So the molecule can move, but it can't rotate or vibrate. At more medium temperatures, then the rotational modes activate. The rotational modes don't require as much energy as the vibrational modes. So more medium temperatures, around room temperature, the atom can move and rotate, but it can't vibrate yet. And then at much hotter temperatures, it can do all 3. It can move and rotate and vibrate.